All right, continuing to understand this theorem 9. So suppose A is 2 by 3 matrix, and then this A transpose A is 3 by 3 matrix, right? And so this is a orthogonal, symmetric and square matrix, and thus it's orthogonally diagonalizable. And so we will have v1, v2, and v3 as also normal eigenvectors. And yeah, we can consider their corresponding eigenvalues of lambda 1 and lambda 2 and lambda 3. And we know that these vectors are all real values, right? Because symmetric matrix will always have this n real root counting their multiplicities. Okay, and so lambda 1, 2, 3, they are all real values, right? And then by properly sorting them in a decreasing order, let's assume lambda 1 is the largest and lambda 2 and followed by lambda 3 being the smallest, right? And now let's consider, we already proved that the linear transformation output of v1, v2, and v3, which are a v1 and a v2 and a v3, and they are orthogonal to each other, which means that so given the inner product between these two different outputs, and then this guy becomes this part, and then this guy is our matrix over here, right? And then this part will become lambda j times vj, and then this is a row vector, and this is a scalar, and this guy is our column vector, and so it can be represented as a lambda j times vi transpose vj, and vi and transpose and vj, and the v1, v2, and v3 are originally also normal eigenvectors of A transpose A, and thus the inner product between the different eigenvectors will always be 0, right? And so we can prove that their outputs are also orthogonal to each other, right? But how about the length of each vector, each output vector? As we saw earlier, let's consider the squared norm of v1, a v1, and then we change it to the inner product between the vector itself, and then we also see a transpose a and the v1, and so it can be changed into lambda 1 v1, and then by changing or moving this scalar to the left, and then we can obtain lambda 1 times v1 transpose and v1, and then this v1 transpose and v1 is changed into the squared norm of v1, which is 1, because v1, v2, and v3 are also normal eigenvectors. Okay, and so this one is the same as lambda 1, right? But here this is the squared norm of a certain vector a v1, right? And so this value, we know that it is always greater than or equal to 0, and thus lambda 1 is greater than or equal to 0 accordingly. Okay, so it means that, given the symmetric matrix of this A transpose A, we know all the eigenvalues are real values, but at the same time, in the case of A transpose A, which is a symmetric matrix, and then all of their eigenvalues are greater than or equal to 0. Okay, so similarly we can also prove that lambda 2 is greater than or equal to 0, and lambda 3, and so on. Okay, so back to these eigenvalues sorted in a decreasing order. We know that all of them are greater than or equal to 0, right? And so here Yeah, some of them are strictly positive and some of them will be possibly zero. And then let's consider the value of an R as the number of non-zero eigenvalues of A transpose A, or the number of strictly positive eigenvalues. So here, let's say R is 2. Okay, so let's assume R is 2, and then it means lambda 1 and lambda 2 are strictly positive. And at the same time, over here is n by n, right? N minus R number of eigenvalues will be just equal to 0, right? So out of n eigenvalues, R number of eigenvalues will be strictly positive, and then n minus R number of eigenvalues will be exactly 0. Okay, let's consider this situation. Okay, and then these outputs of eigenvectors through this linear transformation by A up to those eigenvectors that has strictly positive eigenvalues, and then those output vectors are forming the orthogonal basis for column space of an A. Okay, so this is what this theorem is claiming, which we will see the proof shortly. And then also, if we know that these vectors are orthogonal to each other, and so if they are the basis of column space of an A, and then they are orthogonal basis, and then at the same time, this column space of an A is spanned by R number of orthogonal vectors, right? And so the dimension of this column space, or the rank of an A by definition. Okay, so the rank of an A is just dimension of the column space of an A, right? So this is equal to R, right? Okay, so let's prove this part after prove this last sentence in this theorem 9, right? And then let's consider any vector that is chosen from the column space of an A. Okay, and then by definition, this vector y should be represented as a linear combination of the columns of an A, right? And then the linear combination of the columns of an A is represented as A times x, where x is the linear combination coefficient vector. Okay, so this vector x can be any vector that can work as any arbitrary linear combination coefficient. Okay, and if A is 2 by 3, and then x is three-dimensional column vector, right? And then given this R3, we have this v1, v2, v3 as another also normal basis vector, which are eigenvectors of A transpose A. Okay, and then by using the change of a basis, we can represent this x as a unique representation of this linear combination with respect to v1 and v2 and so on, which are the also normal basis vector for R3. Okay, and then here, again, we assumed R is 2, for example, out of these 3 vectors. Okay, so 2 of them will have non-zero eigenvalue, and the last one will have 0 eigenvalue, right? And then let's just plug this representation into A times x over here, and then it is represented in this form. So in the case of 3 by 3 case, C1a v1 and C2 a v2, so that is corresponding to R. And then we have one additional remaining vector, C3a v3. Okay, and for this guy, we can change it into lambda 3 v3, but what's the value of lambda 3? It is 0 by our assumption that R is equal to 2. So the last one of lambda 3 is 0. Okay, and so this term is actually gone. And then y is represented as a linear combination of uh, these two vectors of av1 and av2. Okay, and what's the dimensionality of them? So they are two-dimensional vector because A is 2 by 3 matrix and the output vector is two-dimensional vector, right? And so this y, which is chosen as an arbitrary vector from column space of an A, is always represented as the linear combination of AV1 and AV2. Okay, so yeah, any vector from the column space of A is always represented as a linear combinations of these two vectors, and let's check whether they are the linearly dependent or not. Because if these two vectors are actually working as the basis vectors, and then uh, they have to not only span the given subspace, but also they have we don't allow any redundancies, or they should be linearly independent. But we already proved that AV1 and AV2 are orthogonal to each other, which just automatically gives this linear independence between these vectors. Okay, so these two are linearly independent, but furthermore they are orthogonal basis vector for column space of an A. So we understood that AV1 through AVR are orthogonal basis for the column space of an A, and thus uh, the R number of basis vectors are forming our column space, and thus the dimension of the column space of an A, or the rank of an A, is actually R, which is the number of strictly positive eigenvalue of A transpose A. Now let's move to the definition of this singular value decomposition, which is analogous to eigendecomposition for the rectangular matrix. So suppose A is a rectangular matrix of the size of an m by n, and then now let's suppose the rank of an A is R, which means we have a R number of strictly positive eigenvalue of A transpose A. Okay, right. And then by definition, the singular values are the square root of the eigenvalues of A transpose A. Okay, so if the eigenvalues of an A transpose A is sorted in a decreasing order of lambda 1 and lambda r and lambda r plus 1 and lambda lambda n, for example, and then these are strictly positive and these are all zeros, and then their square root, okay, their square root is called our singular values of our matrix A, which is denoted as sigma 1, sigma 2, and sigma r, and so on. And then those sigmas corresponding to lambda r plus 1 and so on, they will also be 0. Okay, and then let me pictorially describe this singular value decomposition. So suppose A is an m by n matrix, which is the size of 2 by 3, for example, and then it is decomposed into these three pieces: U sigma V transpose, and these are U and V transpose or V are all square matrix of m by m and also n by n. Okay, and they are by definition of a singular value decomposition, U and V should be orthogonal matrix. And by the way, the definition of this orthogonal matrix is a square matrix, and at the same time it should have also normal columns. Okay, so in the case of a rectangular matrix, for example, like 3 by 2 matrix, we can have these two columns to be orthonormal to each other, right? But in this case, this is not a square matrix, and so this is not called the orthogonal matrix. But here, if we collect another vector in the three-dimensional space, which is still orthonormal to each other among all these three vectors, okay? And then we have a square matrix with the orthonormal columns, and in that case, that matrix is called orthogonal matrix. Okay, so U and V are square matrix containing orthonormal vectors. In other words, they are required to be orthogonal matrix. And now the middle vector called the sigma is actually having the same size as the matrix A, which is an m by n, and yeah, the diagonal matrix is actually defined only for the square matrix, but you can think of this possibly rectangular matrix sigma as the diagonal matrix, where we only have non-zero entries along the diagonal entries, but also for off diagonal parts, we have all zeros. Okay, and here this diagonal matrix, diagonal entry or entries of this sigma should be required to be this positive entries. Okay, so that is the main kind of requirement of the singular value decomposition of an A. And unlike the eigen decomposition, which can either exist or not depending on a particular matrix. Okay, so if the matrix is not diagonalizable, and it means that we cannot obtain n linearly independent eigenvectors, right? So in that case, the matrix is not diagonalizable, and thus the eigen decomposition does not exist. But on the other hand, this is a singular value decomposition. Following this requirement, the singular value decomposition will always exist for any given, possibly rectangular matrix A. Okay, right. And then now let's relate this singular value decomposition with those expressions that we analyzed in the previous slide. So given this representation, let's multiply the matrix V over here. Okay, and in the case of square matrix containing orthonormal columns, which is V, right? And then we know that V transpose V or VV transpose will always be identity matrix, right? And so this part will be gone. Okay, and then now we can obtain this AV is equal to U sigma, right? And then and then here this A times V1, which will form the column vector, the first column vector of the resulting matrix will be the same as the first column vector on the right hand side. But here we have this matrix that has the non-zero diagonal entries, but zero off diagonal entries. So here, if we consider their linear combinations to form the first columns, and then it is just a scale, column-wise scaling of U1, right? And so this result is like sigma 1 U1, okay? And let's see. The second column will be sigma 2 and U2, right? And then what about the last column? It is all 0, right? And so we have the third column of zeros. Okay, so this is the resulting matrix of the right hand side. And then the first column obtained as a AV1 from the left hand side over here by using this as a linear combination coefficient. Okay, that should be the same as this part, first column of the right hand side, which is sigma 1 U1, and AV2 similarly is equal to sigma 2 V2 U2. Okay, over here, by definition, u1 and u2 over here, they are, they are orthonormal vectors, right? Let's start with the eigenvectors of A transpose A as these v1, v2, and v3. Okay, so let's suppose we set this orthogonal matrix V, which is a square matrix containing orthonormal vectors. But here, let's set the columns of V as orthonormal eigenvectors of this A transpose A. Okay, and then we know that AV1 and AV2 and AV3 are orthogonal vectors, right? And then let's imagine kind of normalizing these orthogonal output vectors by its length. Okay, so suppose this sigma 1 over here is set as maybe 1 over AV1. Okay, the norm, 1 over the norm of AV1, and so on. Okay, and then we know this value is actually the square root of lambda 1, because the squared norm of AV1 is obtained as lambda 1, and so its its norm itself is square root of lambda 1. Okay, and so if we simply set this lambda 1 as the square root of, sigma 1 as the square root of lambda 1, and for sigma 2 and sigma 3, which is a kind of normalization factor of the based on the lengths of AV2 and AV3, and so and then once normalizing them and then calling these normalized vector as u1 and u2 and u3. Okay, and then we can obtain these equations, okay, that are those equations obtained from this representation. Okay, and so we started from orthonormal eigenvectors as v1, v2, and v3 of A transpose A, and then once computing their linear transformation output, which are AV1 and AV2 and AV3, they are also orthogonal vectors, right? And so those vectors, after normalizing them to have a unit length, and then those orthonormal vectors, which are u1 and u2 and u3, can be used to form this u1 and u2. But here we assumed that r is 2, right? And so this lambda, let's see, over here lambda 3 is square root of lambda 3, and lambda 3 is 0, right? And so actually this vector is actually 0 vector, and so u3 cannot exist at all, right? And so that way, by just collecting only the non-zero vectors over here, non-zero vectors over here, right? And then we can collect those orthonormal basis vector that forms our matrix U. Okay, and so here we also used the example of r being equal to 2, right? And here one important characteristic is that we know, r is basically the number of positive, strictly positive, or non-zero eigen values of A transpose A, right? And then this number, we proved that this number is the rank of A, or the dimension of the column space of an A, right? And then here, suppose A is um, yeah, 2 by 3 matrix. Okay, so we know that this dimension of the column space of an A is actually less than what? M, right? Or 2. Okay, so yeah, we can also see that R, I mean the upper bound of an R is actually 2, right? And then at the same time, yeah, let's consider this 3 by uh, 3 by 2 matrix. Okay, so here in this case, yeah, R is still having the definition of this, and R is the same as the rank of an A. So in this case, we have two vectors in the three-dimensional space, and then here, what is the number? Yeah, what is the maximum number of an R? So it is still 2 over here. Okay, so 2 comes from here, because here we consider entire three-dimensional space, but we only have the two vectors as our as the basis of our column space, right? And so R is less than or equal to 2. So if it is a m by n, so in the case where m was smaller than n, and then n was 2, and this number is actually corresponding to n. So in this case, m was greater than or equal to n, right? So altogether, the rank of matrix A or R is bounded by the minimum number between m and n. Okay, so it means that non-zero eigenvalues of A transpose A is always smaller than or equal to the minimum number between m and n. Okay, so here, so even if we started from three orthonormal basis vectors, and then the mapping output, or a after transforming a given input vector by using A, and then the output vector is two-dimensional vector, right? And so in the two-dimensional vector, we will only have just two orthonormal basis vector, right? And then we have to have only the two orthogonal or orthonormal vectors, right? And so even if we started from the three vectors, and then we maximally have two orthonormal basis vectors in the output space, and thus out of three, at least one of them should be 0. I mean the eigenvalue should be at least one of the eigenvalue should be 0. Now let's consider another case where A is now 4 by 3, and U is 4 by 4, and sigma is 4 by 3, and V transpose is 3 by 3. Okay, and then as I mentioned, we always start with V1, V2, and V3, which are eigenvectors of A transpose A, right? And then let's consider the linear transformation output by A, and then let's suppose R is 2 this time. Okay, so R is 2, meaning that we have two non-zero or strictly positive eigenvalues of A transpose A, and A transpose A is 3 by 3 matrix, and thus we have last eigenvalue as 0, right? And then let's consider their linear transformation output, and then their squared norm will be the first eigenvalue of A transpose A, and so yeah, this eigenvectors, this eigenvalue uh, is used as this square root of this eigenvalue is used as a scaling factor, and so this guy is our u1 and this guy is our u2, and these are corresponding to these values are u1, these column vectors of u, which are u1 and u2, right? Yeah, just to be concrete, let's say lambda 1 is maybe 9 and lambda 2 is, for example, 4, and then yeah, the singular value of lambda 1 is 3 and this guy is 2, okay? And then what about lambda 3? So by definition, yeah, r is 2 and so lambda 3 is 0, right? Okay, and so the vector length of this guy, I mean this vector, is actually becoming a 0 vector, right? And then the square root of lambda 3, which is a sigma 3, is 0, so this guy will be 0, okay? So we obtained u1 and u2, but how can we obtain these u3 and u4, which are not obtained as the output of this linear transformation by A by using the input vector of the eigenvector of A transpose A, right? So even if we have, yeah, in this case, even if we have non-zero eigenvalues of the last one of lambda 3, right? And then, yeah, we can, yeah, normalize this vector to obtain u3, right? So in this case, we can obtain u3, but yeah, there is no way to obtain u4, right? So we can obtain up to r number of, yeah, orthogonal output vector in, yeah, that fills out the first r number of columns of u, okay? But what about the other vectors? How can we obtain them, okay? And then yeah, so in this representation, so if we imagine this a v and u sigma, okay, and then here in this case, if we have 0 over here when r is 2, okay, and then u times sigma, and then the first column will work as the linear combination coefficient to linearly combine these four, and the second column of sigma will work as the linear combination coefficient, right? And they are only involving, yeah, only involving the first column and the second column, right? And then after this point, we will always see 0, and thus u3 and u4 will never appear in the resulting columns of u sigma, right? So in this representation, u3 and u4, yeah, can be set as any, yeah, set as any vectors as long as they are satisfying this condition of orthogonal u, okay? So up to this point, u1 and u2 are also normal basis vector found as the linear transformation output, and normalizing them, and yeah, they are automatically orthogonal to each other, okay? And then can we find two other also normal vectors that can fill out the rest of the columns of u, okay? And then yeah, we can do this task easily. So the condition or requirement for u3 and u4 is that they are also normal vectors when, yeah, performing the inner product with the u1 and u2, and then the inner product should be also 0. And so we obtained the u1 and u2, right? And then now let's consider this matrix U1 transpose and U2 transpose, and this is our kind of matrix B, for example. And then let's consider this vector x and is equal to 0, and then this vector x should be orthogonal to U1 transpose and also U2 transpose, yeah, U2 transpose, and their inner product should be all 0, right? And so it is like in this case 2 by 4 matrix, and so we have only the two columns, meaning that yeah, we have like two pivots, and so we have two free variables. And so if we compute the null space and the parametric vector form of this matrix B, and then it will give us yeah, 4 minus 2 number of basis vectors for the null space. Okay, and then we can apply the Gram-Schmidt orthogonalization and then possibly, I mean, followed by the normalization, so that the vectors or orthogonal vectors to, can have a unit length. Okay, and so that way we can find two other orthonormal vectors, okay, that are orthogonal to U1 and U2, and then yeah, they have a unit length. Okay, so that's how we fill out U3 and U4. Now let's look at the example. So given this matrix A, so our task is to obtain its singular value decomposition. Okay, so we first form A transpose A, and then obtain its eigen decomposition, or orthogonal diagonalization of it. Okay, and then it will give us orthonormal eigenvectors and also their corresponding eigenvalues as a real values, right? Right, and so given 2 by 3 matrix, A transpose A will be 3 by 3. So it will give us these three orthonormal eigenvectors and also its corresponding eigenvalues. And then taking the square root of it, we can obtain corresponding singular values of the original matrix A. Okay, and then here, yeah, as I mentioned, R, which is the number of non-zero eigenvalues, number of non-zero singular values will be bounded by the mean of m comma n, which is 2 in this case. So even if we have three real valued eigenvalues, but yeah, up to two of them are only non-zero, only up to two of them are non-zero, but the rest of them should be 0. And then yeah, we can compute this AV1 and AV2 as those vectors that forms our U1 and U2 after this kind of normalization with respect to its singular values, right? And so we can obtain these two orthonormal basis vectors, and if we compute the AV3, and then it will give us just the zero vectors. Okay, so by just collecting those two orthonormal vector U's, and then we can form our matrix U, and then yeah, our diagonal matrix, and then also another orthogonal matrix V transpose. Okay. Okay, and so here, yeah, these are called eigenvalues, and at the same time, those vectors, which are the orthonormal columns of U, is called left eigenvectors, and those three vectors, which forms the columns of V or the rows of V transpose, so these are called right eigenvectors. Right singular vectors. Okay, so this is one example. Okay, then now let's consider the four subspace related to the matrix A. So column space of A, or the null space of A transpose, and the row space of an A, and the null space of A. Okay, so let's consider the matrix A as being 7 by 5, and suppose R is equal to 3, and we know that R is the number of non-zero eigenvectors of A transpose A, and also number of non-zero singular values of an A, and also it is rank of an A. Okay, right? And then A transpose A is 5 by 5 matrix, right? So this is 5 by 5, and so it will have 5 eigenvalue and vector pairs, where eigenvectors are also normal, and eigenvalues are all strictly positive or zeros. But here, up to this point, where R is 3, and so lambda 1, lambda 2, lambda 3 are strictly positive, but lambda 4 and lambda 5 is equal to 0, right? Right. And then we studied that AV1 and AV2 and AV3, which are non-zero output vectors, okay? And then once obtaining them and then normalizing them with respect to their lengths, and then we can obtain U1 and U2 and U3, which is in the 7-dimensional space, okay? And then these are also orthonormal vectors, and we studied that these vectors will form our basis vector for the column space of an A. Okay, so the column space of an A. So U1, U2, U3 will provide the orthonormal basis vector for the column space of an A. Okay, and then yeah, back to this example. How did we obtain the rest of the other orthonormal basis vector to form the rest of the columns of U? So that was like, yeah, um, we can just form this U1, U2, U1 transpose, U2 transpose, and U3 transpose, okay? And then multiplying the vector x, and then setting it to 0, and by solving for this homogeneous linear system, and then obtaining the linearly independent vectors, and then followed by Gram-Schmidt orthogonalization, and then we can obtain the other four orthonormal vectors, which are u4, 5, 6, and 7. Okay, and then here those column vectors, yeah, we can also think of yeah, the null space of this, yeah, the null space of this as the orthogonal complement of this column space of an A, right? So we chose the basis vector of this column space of an A, and then formed them as rows of the matrix over here, and then computing the null space of it, and then obtaining the basis of them, okay? And then yeah, those basis vectors will form the orthogonal complement of column space of an A, and then the orthogonal complement of the column space of A can be represented also as the null space of A transpose, which means that, yeah, instead of using this as our matrix over here for this homogeneous linear system, we can simply, yeah, replace it with the matrix A transpose, where each row of this matrix is, each row of A transpose is actually the column of the matrix A, okay? And so this vector x should be orthogonal to this vector, and this vector, and this vector, and so on, which means that this vector x should be orthogonal to each column vector of A, okay? So in that sense, we can use A transpose, or is call yeah the basis vector as rows of this matrix, and these basis vectors are also normal basis vector that we already obtained over here for our column space of an A. Okay, and so U4 through U7, which are four, also normal basis vector for this null space, and then they are also normal basis of the null space of A transpose. Okay. Okay, so here the point is SVD, or singular value decomposition, will give us the also normal basis for the column space, as well as another also normal basis vectors for the null space of A transpose, right? And then now let's consider the singular value decomposition of A transpose. Okay, and then given this singular value decomposition of the original matrix A, and then this SVD of A transpose is simply just transposing this representation of U sigma V transpose. And so let's think of its transpose version, and then V comes first over here, right? And so V transpose is V, and then we have the sigma, and then sigma is transposed, and then U is transposed into U transpose, right? And then now let's think of this sigma transpose, and then this sigma transpose is actually like in this case. So let's suppose we have this sigma, and then A transpose is actually having the size of 3 by 4, and then also sigma will also have the size of 3 by 4, right? But here the sigma will have only will have non-zero entries only along the diagonal entries, right? And so even if we transpose it, and then the matrix size change from 4 by 3 to 3 by 4, but the diagonal entries will not change at all. Okay, so in that sense, it's really sigma transpose over here, but so this is wrong actually, but this representation, but this guy has the same size as A transpose, but also it will have the diagonal entries which are exactly the same as the diagonal entries of sigma. Okay, and so here let's consider this, and also V and U are still orthogonal matrix, which are square matrix containing also normal column vectors. Okay, so in this case, similar to the previous case, we consider calling this matrix as B, and then we consider B transpose B, right? And then that is actually A transpose, and then this is now, let's see, A transpose A is 5 by 5 matrix, and then this P transpose B, or A transpose, is 7 by 7, and it's still a symmetric matrix. And we have these 7 pairs of eigenvalue and eigenvectors, where all the eigenvalues are real and eigenvectors are also normal to each other. Okay, and then now those singular values, or this eigenvalues of A transpose, is actually represented over here. So those equations are obtained from like A transpose and U is equal to V and sigma transpose, okay, by multiplying U over here and U over here. Okay, and then by just equation in a columnized manner, so this is the first column of this matrix, and this is the first column over here, and the second column and the third column. Okay, and then if we start from these u1, u2, and u3 and so on as eigenvectors of this guy, A transpose, okay, and then A transpose u1, and then obtaining it as a normalized, normalizing it so that this vector is having the unit length, and then yeah, we can obtain v1 and their corresponding length value as a sigma 1, okay, and then yeah, we can do the same thing on the other equations. Okay, so here the point is u1, u2, and u3 are actually these eigenvectors of A transpose, which are associated with non-zero eigenvalues of lambda 1 and lambda 2 and lambda 3, and after then lambda 4 through lambda 7, they are all zeros, okay, yeah, because r is set to be 3, and so yeah, lambda transpose will only have the first three non-zero diagonal entries, but after then we will always have zero entries along the diagonals. Okay, so here, yeah, based on this property, okay, based on this property, we can also, yeah, we can also relate, yeah, we can also relate this v1, v2, and v3 as the orthogonal or orthonormal basis, orthonormal basis of column space of what? A transpose, right? Because we originally used A transpose, right? And then v4 and v5 and so on, v7, okay? So these vectors will work as the orthonormal basis of the null space of, yeah, the null space of A, okay? So overall, once obtaining this singular value decomposition of a given matrix A, and then suppose our rank R is 3, and then the first 3 columns of U will provide the orthonormal basis vector of column space of an A, and the rest of these vectors will provide the orthonormal basis of the null space of an A transpose, and at the same time the v1 through v3, which are the first R number of singular vectors obtained from v over here. So these vectors will work as the orthonormal basis vectors of column space of an A transpose, and at the same time v4 through v7. Yeah, v4 through v7 will be orthonormal basis vectors of the null space of an A. But here, let's see. Yeah, there was a something wrong over here, and so the null space of an A transpose is actually belonging to 5-dimensional space, and so our matrix, let's see, our matrix U is 7 by 7. Yeah, the null space of an A transpose is still belonging to R7, but here, yeah, the column space of an A transpose is R5, and also the null space of an A is also belonging to R5, and so yeah, I was wrong over here in terms of the number of the remaining vectors of V's. So v4 and v5 which are the last two column vectors of V, which is like 5 by 5 matrix, right? And so V4 and V5 are providing the orthonormal basis vectors of the null space of an A. Next, let's discuss additional items to include in the invariable matrix theorem. So we now consider the square matrix of an n by n matrix. And so here we know that this matrix should have n linearly independent column vectors, right? So in that case, the dimension of the column space of an A, or the rank of an A, should be the same as n, right? So this is the equivalent condition for the matrix A to be invariable, right? So in this case, what will be the dimensionality of the orthogonal complement of this column space of an A? So in this case, so it will be, the dimension of the orthogonal complement should be like n minus the dimension of the column space of an A, right? And so this is an n, and so it should be 0. So what's the subspace with the 0 dimension? And that is just containing 0 vector, right? All right. And then what about the null space of an A? So here the point is the rank of an A is actually the dimension of the column space, right? And that was denoted as R in the previous case, right? So again, R was initially considered as the non-zero eigenvectors of A transpose A, but here when considering the eigen singularity decomposition of an A transpose, which is obtained simply by transposing the original singularity decomposition of an A, okay? And then here the non-zero eigenvectors of an A transpose A is the same as R, and then this number is the same as the non-zero eigenvectors of A transpose over here, okay? And then this R, or this number of these three eigenvalues of A transpose will work as the orthonormal basis vectors of column space of an A transpose. And so here the column space of an A transpose is actually called the row space of A, right? And so the row space of A and its dimension, okay? And then this dimension is the same as the dimension of the column space, right? So these are all equal to R, okay? So if in case the matrix is invariable, and then the dimension of the column space will be n, and so the dimension of so we have to move this part over here, right? Okay, and then an invariable matrix has the rank of an A as an R, which is also the same as dimension of the row space of an A. Okay, and so this guy, row space of an A, and its dimension should be n. That is the equivalent condition for the invariable matrix A, and so, and also in case the dimension is an R, and then the subspace will be the same as the entire n-dimensional space, okay? And also the null space of an A and its orthogonal complement is actually the same as, let's see, it is the column space of A transpose, right? and so it is also the row space, and so these two are the same. Okay, and the last item in our invariable matrix theorem is that this R should be simply set as n, right? So what was R? R is the number of non-zero eigenvectors of A transpose A or AA transpose. But at the same time, this R is the same as the number of non-zero singular values, right? So A has n non-zero singular values, right? In that case, it means R is equal to n, and R is the rank of matrix A. Okay, so invariable matrix will have n non-zero singular values, right? And then now let's move to the reduced form of an SVD. So this is another example of the singular value decomposition where m is larger than m is larger than n, and then we have m by m matrix U, which is orthogonal matrix, and sigma, which is the same size as matrix A, and then V transpose, which is an n by n matrix whose rows are also normal vectors, right? And so here let's consider the multiplication between these two, sigma and V transpose. And since multiplying this kind of diagonal matrix on the left of this matrix, and then it will perform this row-wise scaling, right? And then what about this part? So this part will work as the linear combination coefficient for each row on the right matrix, but here we have all zeros, right? And so altogether, if we multiply these two, and then we will obtain sigma 1, and then their row-wise scaling of V1 transpose, sigma 2, and V2 transpose, which are just a row-wise scaling, okay? And then sigma n times Vn transpose, okay? And then now, what about the other ones? So we have m rows over here, and then so far we have n rows, and then the rest of the rows will be just zeros, right? Because we are using completely zero linear combination coefficient to combine those rows on the right, right? And then we have this m rows of the matrix that has m rows, and so we have m columns, right? And then we can simply apply the sum of rank 1 outer product for this matrix multiplication, and so u1 and this guy, okay? So this outer product and this outer product and this outer product, okay? But after n plus 1's rows, it's a completely zero, and then that will be multiplied with the n plus 1's column in this matrix. But because we are multiplying with the zero row vectors, and then it will be simply all zeros, right? So it will be all zeros. Okay, and then we have this kind of outer product, right? Sum of an outer product. Okay, and then now let's consider the rank of matrix A is strictly smaller than this n over here. Okay, so here up to r number of singular values will be non-zero, and after then we will have zero, right? And then by applying kind of similar tricks of viewing or rewriting it in the form of sum of rank 1 outer product, right? So we have only r number of non-zero entries, but all zero entries after then, right? And then if we perform, or if we multiply these two matrices and then representing it as the sum of rank 1 outer products, and then it is actually becoming just the sum of r number of these outer products, right? Okay, so given this outer product, let's reorganize this matrix. Okay, and so we have r number of outer products, and then how about this? Um, yeah, because we have r number of an outer products, we just collect these r number of column vectors u1 through ur. Okay, so let's form this matrix in the left, on the left, and then now we form our matrix in the middle as having r by r matrix, where our diagonal entries are sigma 1, sigma 2, and sigma r. Okay, and then now how about the matrix multiplied on the right? And that is like v1 transpose, v2 transpose, and then vr transpose. Okay, so this is our new matrix. Right, and so let's denote this matrix as ur and sigma r and vr transpose. And here, this is called the reduced form of singular value decomposition, or SVD. So in this case of reduced form, so ur and vr is no longer be the square matrix, okay? But instead, ur is given A being m by n matrix, and then ur is m by r. And what about sigma r? So this is actually the square matrix. Really, it became diagonal matrix. And then this guy is r by n. Okay, so this representation is called reduced form of SVD. So in this form of a reduced SVD, so the intuitive effect is that we are actually ignoring these parts, okay, which are also normal basis of the null space of an A transpose or the null space of an A. Okay, so we are only using the first r columns of U and the first r rows of V transpose. Okay, so that way we are just ignoring these parts. Okay, so we don't actually need to solve for this null space or the solution for this this homogeneous linear system, right? So that is our reduced SVD. This reduced SVD can also be viewed from this perspective. So originally, suppose we have U sigma V transpose, and then originally U is a square matrix containing also normal column vectors, and V transpose is also a square matrix. Okay, and then here let's consider the first r columns of U and then the rest of our columns, and also V, which is the original V used as its transpose over here, and then V, the first R number of columns of V's, and also it should be V over here, and so the rest of the column vectors of V. Okay, and so we can represent these two parts. So A is m by n, and so UR is m by r, and this part is m by m minus r. And here is actually m by n, but here we consider this r by r matrix as our D, and over here this 0 is r by n minus r, right? Then what about this part? So this part is m minus r by r, okay? And then the remaining part over here, it is m minus r by n minus r, okay? So it's all composed of 0. Right, and then we have this part as r by n, and here n minus r by n, okay? And so we can think of this partitioned representation of this matrix, and so here, yeah, we can just treat it as a scalar, and so let's perform the matrix multiplication on the last two, and then we just perform this inner product, okay? And then it is multiplied with the 0 over here, and so the inner product will be obtained as D times VR transpose, and then yeah, plus actually 0 times V n minus R transpose, but this is 0, right? So we only have this part, okay? And then the next part is like multiplying these two 0 row vectors and this column vectors, and so it will be simply 0, right? And so we will obtain 0 block over here, okay? And then over here we have this guy, right? And then we can apply this sum of rank 1 outer product and this part times this part, right? And then also this part times this part, which is 0, and then they are added together, and so we can see that only the first outer product is non-zero, and so UR and D and VR transpose is the final result, okay? And so here, yeah, this is UR times D and VR transpose. So in that manner, we can also obtain this reduced SVD form. Okay, so this is by using the tricks of partitioned matrix and their multiplications. Okay, so this is almost the last part. Suppose we have the reduced form of SVD of A, and UR and D and VR transpose. Okay, so A is a M by N, and then the rank of an A is R, and then this UR is M by R, and what about D? D is R by R, right? And then this guy is R by N, right? Okay, and then yeah, something called a pseudo inverse. It's like kind of fake inverse. Okay, so intuitive meaning is that it's a kind of a fake inverse, and yeah, when discussing the inverse matrix of an A, we only considered the square matrix, right? But here we can kind of generalize this the notion of an inverse matrix, which was originally defined only for the square matrix, and then we can kind of extend it to the notion of an inverse that can be defined for even for the rectangular matrix. Okay, rectangular matrix A, which has the size of an m by n matrix, and then the pseudo inverse is defined as follows. So pseudo inverse is represented as A plus. I don't know why it's represented in this form, but here, yeah, we actually change the order between these matrices, and then we first bring this VR, and then the inverse and the UR transpose. Okay, so we change this order. Okay, and then D is actually is changed into D inverse, and D is over here. D is really this part, right? R by R matrix, where the diagonal matrix are strictly positive, because we assumed R number of strictly positive eigen singular values. And then if we have D over here in this form, and then D inverse is simply the same size of matrix where the diagonal entry is the reciprocal of the original singular values. Okay, so that is the definition of pseudo inverse. And let's think of the size of this pseudo inverse. And then this guy is like n by r, and this guy is still r by r, and this guy is r by m. So the pseudo inverse of m by n matrix A is having the size of n by m. So the pseudo inverse has the size of the which is same as the A transpose. Okay, so this is called the pseudo inverse. And now let's check our book, and then see the use case of this pseudo inverse, right? And then yeah, this guy is actually the pseudo inverse, right? And then now let's consider the least square solution of ax minus b and 2 norm squared, and we want to minimize it with respect to the vector x. And then this solution was called the x hat, and this guy was obtained as the normal equation, right? Normal equation. And then also at the same time, let's consider this ax hat, and this is actually the orthogonal projection. So let's see. Six point five. So this ax hat is actually the orthogonal projection of B onto this column space of an A, right? So this is actually the orthogonal projection. And yeah, what was the solution for this least square solution? A transpose A inverse A transpose B, right? And then if we further multiply A, and then we obtain A times A transpose A inverse A transpose B. Okay, and so this part is the linear transformation defined by this standard matrix. Okay, and then here, it is actually the projection matrix that orthogonally projects B onto the column space of A. Okay, and then here given the matrix A, let's consider the column space of an A, and then suppose from the SVD we obtained also normal basis vectors for this column space of an A. What was that? And that was the first R number of singular vectors contained in our U, right? Okay, and so uh, if the matrix rank of an A is, I mean the rank of this matrix A is R, and then this basis is U1 and U2 and UR, right? Which is the first R columns of U from the SVD. But here, these are also normal basis vectors, right? And then AX hat is orthogonal projection, or this guy is a A transpose A inverse and A transpose B, right? And so this guy is the orthogonal projection of B onto the column space of an A, right? So projection of B onto the column space of an A, right? And then suppose we have the orthonormal basis vector for this column space that are where this B is orthogonally projected onto the space. And then in this case, so yeah, this guy is our matrix UR, right? By having these basis vectors as our columns of UR. And then what is the projection matrix? That projection matrix will be UR, UR transpose, and B, right? So again, UR contains columns as also normal basis vectors for column space of an A, and so in case we have also normal basis vectors, and then the projection matrix can be simply obtained in this form, UR transpose. Okay, and then now here in this example, it is claiming that the least square solution can be also obtained. I mean, it can also be obtained in, as this formula derived from the normal equation. But suppose we obtained this URD and the VR transpose as a reduced SVD of A, and then this B hat, which X hat, which is like corresponding to this part, so that can also be represented into this form: VR and the inverse and UR transpose and B, and this blue part, okay, this blue part is actually what we defined as the pseudo inverse of matrix A. Okay, so originally suppose A had like 5 by 3 matrix. Okay, so we have 5 equations, but and the 3 variables, and then 3 variables, and then like minus, given 5-dimensional vector B, and then we want to minimize it, right? So this is our original least squares, right? And then we have matrix A, and then we have the singular value decomposition over here as a reduced form, and the A plus, or A pseudo inverse of an A, is 3 by 5, right? And then what about B? So B is this vector, so this is a 5 by 1. Okay, and so we can obtain 3 by 1 output, or 3-dimensional column vector for X hat. Okay, so we haven't proved that this representation is actually our least square solution, but let's verify or confirm this is indeed the least square solution by just plugging in this orthogonal projection of AX hat, which is like, which is the orthogonal projection of B onto the column space of an A. Okay, and then A is represented in this form over here, and then the pseudo inverse A of an A is represented in this form, and then B is over here. So here we have this part, VR transpose and V, and the VR Yeah, VR is uh, n by r, having the size of an n by r. So here it has r number of orthonormal columns, right? And so this guy is becoming identity matrix, right? And then here, uh, let's consider this a D and a D inverse. So what was D and D inverse? Let's see. As I mentioned over here, if we have D like this, and then D inverse is defined in this form, and so D and D inverse will be also obtained as identity matrix. So here, this part is also becoming identity matrix. And then now the remaining part is UR and UR transpose times B, right? And so this is indeed the orthogonal projection onto the column space of an A, where the columns of U are the orthonormal basis vectors of the column space of an A. Okay, so in this manner, we verify that when setting x hat, which is our least square solution, as the pseudo inverse times B, okay, in this case, AX hat, which is corresponding to the orthogonal projection of B onto the column space of an A, okay, and then that representation is properly obtained or successfully obtained as expected. And so we confirmed that this representation is indeed the least square solution.